This is a full paper walkthrough for Edexcel GCSE Maths Paper 3 from 2022. For each question in the paper, I will give a brief overview of what topics are involved in the question and then give my full worked solution. Question 1 is looking at Pythagoras' theorem. We're given a right angle triangle with a short side 4 centimeters, an unknown short side of x centimeters, and a hypotenuse of 8.5 centimeters, and we're asked to find the value of x. So of course we just need to apply Pythagoras' theorem, that is a squared equals b squared plus c squared, where a in this case is the length of the hypotenuse, the longest side of the right angle triangle, and b and c are the two shorter side lengths. In this case, of course, we're looking for a short side, so we're going to use c, so we just have to rearrange this equation to make c a subject. So in this case, we just get c squared equals a squared minus b squared, and so c, which obviously is equal to x, is equal to the square root of a squared minus b squared. So that's the square root of 8.5 squared minus 4 squared, which gives us 7.5. Of course, we don't have to write centimeters here because the answer is x centimeters, not just the side length of x here. Question 2 has two different parts, both of which are looking at these different algebraic expressions. 2a specifically is looking at evaluating quadratic expressions. So we're told that t is equal to 4m squared minus 11, and we're asked to find the value of t when m is equal to minus 3. So all we're going to do here is substitute minus 3 in for m in this expression. So we get t is equal to 4 times minus 3 squared minus 11. Of course, we know that minus 3 squared is just 9. So we have 4 times 9 minus 11. We know that 4 times 9 is 36. So t is equal to 36 minus 11, which is 25. And that's our final answer. Question 2b is about changing the subject of an expression. So when we say the subject of an expression, we mean any variable that is given basically on its own, equal to some expression of another variable or other variables. So in this case, initially we have d as the subject because we just have d on its own on the left hand side equal to 3p plus 4. And our objective is to make p the subject. So we want p on its own, no coefficient, no adding or subtracting anything. So we're just going to start rearranging the equation. So first of all, we're going to subtract 4 from both sides of the equation to get 3p equals d minus 4. And then we're going to divide both sides by 3. That's to get rid of this coefficient of 3 here. So we're going to end up with p is equal to d minus 4 in brackets divided by 3. And that's our final answer for p. Question 3 is a mix of an algebraic word problem and also a question about ratios. So we're told that Rick, Selma, and Tony are playing a game with counters. Rick has some counters, Selma has twice as many counters as Rick, and Tony has 6 counters less than Selma. We're then told that in total they have 54 counters, and that the number of counters that Rick has to the number of counters that Tony has as a ratio is equal to 1 to p, and we're asked to work out the value of p. So my first big tip here is that if we have this sort of situation where we have a bunch of unknown values, we're going to try and label them in relation to each other. So we're going to say that this value of some counters that Rick has, we're going to call that x. Selma has twice as many as Rick, so that's going to be 2x, and Tony has 6 less than Selma, so that's going to be 2x minus 6. We know, of course, that altogether they must have 54 counters, so if we combine all of these algebraic expressions together, we get that 5x minus 6 is 54, and so 5x is equal to 60. We've just added 6 to both sides of this expression. And then by dividing both sides by 5, we get x equals to 12. So Rick's got 12 counters. Tony has 2 times 12 minus 6, which is 18. Obviously, Rick and Tony being the subject of the second half of this question. So now we just have to put 12 to 18 in a ratio in the form 1 to p. We can see that to go from Rick's side of the ratio, from 12 to 1, divided by 12. So of course, to keep the ratio explaining the same concept, we need to also divide Tony's side by 12 as well. If we divide 18 by 12, we're going to get 1.5, and so p in this ratio is equal to 1.5. Question 4 is a classic price comparison word problem. So we're told that Joe's going to buy 15 rolls of wallpaper, and there's 2 shops from where she can buy this wallpaper. At the first shop, the pricing is 3 rolls for £36, and at the second shop, it is £70 for 5 rolls, but with 12% off this normal price. So we're asked from which shop should she buy the rolls if she wants to, spend the least money. And so we need to find the price of 15 rolls of wallpaper from both shops. So at the first shop, Chic Decor, 3 rolls cost £36. So obviously, to get to 15 rolls, we need to multiply this deal by 5. So 15 rolls for £180. That's our price for the first shop. For style papers, we have 5 rolls for £70. So we want to multiply this deal by 3 to get 15 rolls for £210. And then we apply the 12% discount. Because discount obviously is going to decrease, that means that our multiplier is going to be 0.88, so that's 1 minus 0.12. And so 15 rolls for £210 times 0.88, so 15 rolls cost £184.80. Obviously, this means Chic Decor is cheaper, and so she should buy the wallpaper from this first shop. Question 5 looks at frequency polygons. So we're given a table of lengths of some pieces of string with 10 centimeter intervals from 0 to 50 and their respective frequencies. Amos draws a frequency polygon for the information in the table, and we can see here, there's a frequency polygon. We're then asked to write down 2 mistakes that Amos has made. So let's talk about how we actually draw a frequency polygon. So we have this table of data here, and what we want to do, of course, first is draw axes that have got the correct units. So our x should range from about 0 to just after 50, and our y should range from 0 to somewhere past, but not that far past 50 as well. We then want to plot each point on the x midpoint, so the midpoint of each interval. So for example, for 0 to 10, 5, for 30 to 40, 35, etc. And the y, of course, should be the given frequency. So for example, we can see here that for the first interval, we're using the x midpoint, 5, and the correct frequency of 15. If we look through all of these points, however, we can see that the last point is plotted at 50 when it should be plotted at x equals 45. So that's the first mistake. Final point is x equals 50, should be at the midpoint of the last interval, which is 45. And then going back to our original point about drawing the axes correctly, we can see that the y-axis actually skips over the 40 demarcation. So it should, of course, go 0, 10, 20, 30, 40, 50. Again, should have a bit of space above the maximum point, but here it completely skips the 40 point. So that's the second mistake that Amos has made. Question 6 is about kinematics, or as it might be more commonly referred to, speed, distance, and time. So we're told that Jessica runs for 15 minutes at an average speed of 6 miles per hour. Then she runs for 40 minutes at an average speed of 9 miles per hour. And we're also told that it takes Amy 45 minutes to run the same total distance that Jessica runs. And so we're asked to work out Amy's average speed in miles per hour. So obviously, because it refers to the total distance that Jessica runs, obviously we're going to have to work out what that total distance is. So we're going to do that first. So Jessica, 15 minutes, obviously is equal to a quarter, or 0.25 of an hour, at 6 miles per hour. Of course, we can think back to our equation. Speed equals distance divided by time. And so distance is going to equal speed times time. So that's obviously here 6 miles an hour multiplied by 0.25 hours gives us 1.5 miles. Then for the next 40 minutes, it's obviously equal to 2/3 of an hour, and that's at 9 miles an hour. So again, speed multiplied by time gives us a distance of 6 miles. So altogether, her total running distance is 7.5 miles. Now we can again use our speed equals distance over time, but this time in its original format to find out Amy's average speed is going to be the distance she runs divided by the time she takes to run that distance. And so obviously that's the same total distance, 7.5 miles, divided by 45 minutes that we're told here. Obviously to do miles per hour, we have to change this time scale to hours. So we do 7.5 miles divided by 2/3 of an hour. And obviously it's important if you're doing this on a calculator, you have this 2/3 in brackets, so there's no confusing multiplication, division, etc. And that's going to get us an average speed of 11.25 miles per hour, which makes sense because obviously this is going to take Jessica
what, 55 minutes, and this is going to take Amy 45. So it makes sense that she'd be running on average faster than Jessica did at any point. Question 7 looks at compound area. So the diagram shows the rectangle STUV. We're told that TQU and SRV are both straight lines, and all the measurements given are in centimeters. We're also told that the area of this trapezium QUVR is a centimeter squared, and we're asked to show that a is equal to 2x squared plus 20x. So obviously, we sort of understand immediately, really, that we're asked to talk about the area of this trapezium, and that's given as a. So really, we want to show that the area the area of this trapezium, is equal to this expression also, which obviously requires finding out some of the side lengths of this trapezium. So if we immediately we can see, we know obviously this is a STUV is a rectangle, and so these opposite sides must have the same length. So if down here we have 3x plus 5, up here we must have 3x plus 5 also. So obviously if this is 2x here, then this must be x plus 5 here, QU. And UV must be the same as TES, so that's just 4x. So we know that the area of a trapezium is a plus b times h divided by 2. H is the height, this sort of the side opposite the slanted side, and A and B are the two sort of varying length parallel sides. So here we're going to have x plus 5, that's A plus B, times by 4x, that's our height, divided by 2. Obviously this becomes x plus 10 times 4x divided by 2. We can expand out these brackets to get 4x squared plus 40x. This is all divided by 2. I know it's not made very clear. Obviously dividing both by 2, we can then get 2x squared plus 20x. We know obviously from the wording of the question that this is our a centimeter squared, and so we've shown what we need to show. Question 8 is a multi-parter, and part A specifically is looking at the properties of linear equations. So we're told that an electricity company charges the same fixed amount for each unit of electricity used, and David uses this graph to work out the total cost of the electricity that he's used. Part A, looking at the gradient, specifically says work out the gradient of this straight line. So firstly, we're going to recall that the gradient of a straight line is the rise over the run, the rise being the change in y and the run being the change in x over the same interval. So we can see we're going to use the whole width of the graph. We're going to use all the data available to us to get the best estimate. And so we're going to see here there's a change in x of 140 and a change in y of 19.6. So the gradient is going to be 19.6, our change in y, divided by 140, our change in x, which is equal to 0.14. And part B of question 8 asks a bit of a peculiar question. It says, what does the gradient of this line represent? So when we are faced with a bit of a new question like this that isn't really, commonly repeated among different papers, it's important to think about the units. So we can see our x axis here describes the number of units of electricity used, so clearly that's not that well detailed, and the y-axis is the cost of those units of electricity. Now remember from part A that the gradient of a line, what we're looking at here, is the change in y over the change in x. So in this case, it's going to be the cost divided by the number of units used. So if we think about what this would mean, cost divided by units. When we divide units, that's the same as saying per. If we do meters divided by seconds, that's meters per second. So in this case, it's pounds per unit. So in this case, the gradient is the cost of 1 unit of electricity. Question 9 is another multi-parter, both parts being on indice laws, and part A specifically asking us to simplify this expression and express the answer as a power of 10. So we begin with the square root of 10 to the 360 divided by 10 to the 150 times by 10 to the 90. So firstly, we're going to make this denominator into one term. If we multiply powers of the same base, then we add those respective powers. So 10 to the 150 times 10 to the 90 is 10 to the 260. Conversely, if we divide powers of the same base, then we subtract the respective powers. So 10 to the 360 divided by 10 to the 260 is equal to 10 to the 100. And finally, when we square root some given power, we halve the power. And the reason why we can do that is because the square root operator is the same as saying uh, the power of a half of that given base. So we could say, for example, 10 to the power of 100 square rooted is equal to 10 to the power of 100 all to the power of a half. And we know that if we do the power of a power, we multiply said powers. And so in this case, we get 10 to the power of 100 times a half, which is equal to 10 to the power of 50. And part B of question 9 continues with the theme of indices, but goes into a different format of someone making a mathematical statement that's incorrect, and we have to correct it. So Liam was asked to express 12 to the power of 50 all squared as the power of 12. Liam wrote that 12 to the power of 50 all squared is equal to 12 to the power of 50 squared, which is equal to 12 to the power of 2500. Liam's method is wrong, and we're asked to explain why. So you may have noticed in my wording there's a significant difference here. So 12 to the power of 50 squared has this squared outside of the brackets. So this is implying that it's 12 to the power of 50 times 12 to the power of 50, which we would know from our indice laws. We add those powers, we multiply the same base, so we get 12 to the power of 100. This term here is a very different statement. This is saying 12 to the power of 50 squared, where it's the 50 that is squared and not the 12 to the power of 50, which is obviously very different. So the mistake is in this logical jump here, as I've said over here. Question 10 is looking at compound interest with the slight twist that the interest is not the same year on year. So we're told that Jane bought a new car 3 years ago. At the end of the first year, the value of the car had decreased by 12.5%, and the value of the car then decreased by 10% per year for the next 2 years. At the end of this 3 year period, the value of the car was £17,010, and we're asked to work out the value of the car when Jane bought it 3 years ago. So as normal, if we have some sort of unknown value we want to calculate, we're going to assign it as X. So we're going to say the car was worth X pounds when first purchased. So after the first year, the value decreased by 12.5%. And now as a multiplier, this would be 0.875. Remember the key word of here is decrease. And so we take away 12.5% from 100%, which will get 87.5%. And of course, as a multiplier, this is 0.875. So the value after the first year is 0.875x. It then decreases by 10% per annum for 2 years. And as a multiplier, this is going to be 0.9 per year. Obviously, we follow the same logic as previously. So the final value is going to be 0.875x, that's after the first year, times 0.9, that's after the second year, times 0.9, that's after the third year. So that's 0.70875x. So we can say that 0.70875x, that's our value after 3 years, is equal to 17,010. That's what we've been given as the value of the car after 3 years. And so if we divide both sides by the coefficient of x, 0.70875, we can isolate x. We get x is equal to 17,010 divided by 0.70875, which gives us an initial value of £24,000. Question 11 looks into combinatorics, and this is an area of maths that can get quite complex, but at GCSE is always kept very simple. We're just given a list of different parameters like shirts, pairs of jeans, and jackets, and we're asked to construct combinations, hence combinatorics, such as Raheem choosing to wear an outfit that involves one shirt, one pair of jeans, and one jacket. And we're asked to work out how many different outfits Raheem can choose. So as written over here, this is quite simple. With any of these 16 shirts, he could then choose to wear any of 5 pairs of jeans and then any of 3 jackets. So we can think 16 times 5 would make the number of shirt jeans combinations he has, of course being 80, and then multiplying again by 3 is how many jackets he could then obviously wear with those shirt jean combinations. So multiply that by 3 and we get the 240 unique outfits Raheem could choose from. So question 12 is looking at trigonometry, and we're given two right angle triangles, ADC and ABC, and told that the length of the side DC is 8 centimeters, the size of the angle ADC is 45 degrees, and the size of the angle ABC is 20 degrees. And we're asked to work out the length of the side AB. So the first thing we're going to do in these sorts of trigonometry questions is label the triangles. So we have the hypotenuse of both triangles, we have the adjacent sides to the angle of both triangles, and the opposite side to the angle of both triangles. labeled here. We can see that we've got AC as a common side between these two triangles. So if we can find the length of that, we can use the information from this triangle to determine things about this triangle. So that's what we're going to do first. So we know the adjacent DC, and we also are trying to find the opposite AC. So we have O and A, and so we're going to use TOA. It's out of SOHCAHTOA. So that's tan 45 is equal to O, which we don't currently know, divided by 8. Multiplying both sides by 8, we get that O, which is obviously AC, is equal to 8 times tan 45. And given that tan 45 is 1, we have AC is 8 centimeters. Now we're going to use this knowledge to work out things about this triangle. So we've got the opposite, we're looking for the hypotenuse, and so we're going to use SOH from SOHCAHTOA, so sine of 20, the relevant angle, is equal to 8, which is obviously the opposite, divided by x, which is our hypotenuse. If we rearrange this, we can see that x is equal to 8 divided by sine of 20. We can just do that by multiplying both sides by x and then dividing both sides by sine 20. And so we get x is equal to 8 divided by sine 20, which is 23.4 centimeters. So question 13 is looking at column vectors. So we're told that A and B are vectors such that A is equal to 2 minus 3, and 3A minus 2B is equal to 8 minus 17. And we're asked to find B as a column vector. So the important thing to remember here is that we can treat vectors just like regular algebraic objects. So if we say 3a minus 2b minus 3a, that's going to give us minus 2b. If you can see, we just cancelled out the effect of applying the vector 3a here. And from this expression, if we just divide both sides by minus 2, as we could in algebra, we get that b is equal to 3a minus 2b minus 3a, all divided by minus 2. If we then substitute in the values of these vectors, we know obviously that 3a minus 2b is 8 minus 17, and minus 3 times a is minus 3 times 2 minus 3, all divided by 2. Obviously, if we then, we know that if we multiply a vector by a scalar, we just sort of multiply each component by that scalar. So this becomes 6 minus 9, again, still divided by minus 2. If we subtract vectors, we just subtract each component from respectively. So we're going to get 2 minus 8, we've just done 8 minus 6, and minus 17 minus minus 9. So we get 2 minus 8 all over minus 2. And finally, if we divide a vector by a scalar, we just divide each component by that scalar. So 2 divided by minus 2 is minus 1, and minus 8 divided by minus 2 is 4. So the value of b is minus 1, 4. And obviously, importantly, in the exam, you should write this as a column vector. It's only not written as column vectors through this because just for brevity. Question 14a is about factorising quadratic expressions. And so we're asked to factorise 4p squared minus 36. So when we hear the word factorising, that is taking simple expressions and putting them in sets of brackets. This particular expression is what's called a difference of two squares, where we have a 0p coefficient, we've got no p term involved, and so the brackets are going to be positive and negative. We're going to have ap plus b, and then cp minus d. Now we need a times c to be 4 to get this 4p squared term, and we need b times d to be 36 to get this minus 36 term. And also, to make sure there's no p coefficient, we need to make sure that AD, which is going to make part of the p coefficient, and BC sort of basically cancel each other out, right? And the easiest way to do this is make A equal to C and B equal to D, because then we're going to get basically the same thing for just, plus and minus. That will cancel out the p coefficient. And so, what number can we multiply by itself to get 4? For 4p squared, that's 2. And what number can we multiply by itself to get 36? That's obviously 6. So A and C are 2, and B and D are 6. And so when we factorize this expression, we get 2p plus 6, 2p minus 6. 14b is about expanding linear brackets, and we're asked to show that brackets m plus 4 times brackets 2m minus 5 times brackets 3m plus 1 can be written in the form am cubed plus bm squared plus cm plus d, where a, b, c, and d are all integers. So effectively, we're just going to expand out these brackets into this sort of expression. And so the easiest way to do this is to expand out one pair of brackets, leaving the other one alone. And then once we've got a quadratic equation from those, then expand out the remaining set of brackets into that. So we're first going to multiply these first two brackets. So we're going to obviously multiply m by 2m to get 2m squared, m times minus 5 to get minus 5m, 4 times 2m to get plus 8m, and 4 times minus 5 to get minus 20. So then we get this expression here. And before we expand out this last bracket, we're going to just simplify the first expression. So obviously we can see minus 5m plus 8m gives us plus 3m. So we have 2m squared plus 3m minus 20 times brackets 3m plus 1. Then we just multiply out the last bracket. So 2m squared times 3m is 6m cubed. Uh, then 3m times 3m is 9m squared. Minus 20 times 3m is minus 60m. 2m squared times 1 is 2m squared. 3m times 1 is 3m. And minus 20 times 1 is minus 20. But then it's going to simplify this expression again by collecting up like terms. So we've got the 6m cubed already, just that's the only m cubed term, that's fine. We have 9m squared plus 2m squared, so we get 11m squared, minus 60m and plus 3m, so we get minus 57m. And obviously, in terms of just numbers, no m's, we've just got minus 20, so we're left with minus 20. So our final expression is 6m cubed plus 11m squared minus 57m minus 20. So a, b, c, and d clearly are all integers. Question 15 merges the topics of similarity of shapes with circle theorems. So we're given that P, Q, R, and S are 4 points in a circle, told that PXR and SXQ are straight lines, and we're asked to prove that the triangle PQX and SRX are similar. So when we say similar shapes, we mean that we can map one onto another just by rotating, reflecting, and scaling it. So in the context of a triangle, this just means if we can prove all three angles are the same, corresponding angles, then the two shapes must be similar. So using circle theorems, we can see that we've sort of got two chevrons starting at QR, going to P and S. And so these angles at the circumference must be the same. So QPX is equal to XSR. We can then flip that around and we can say we've got two chevrons originating from P and S going to Q and R. And so PQX, this angle here, must be equal to SRX, this angle here. Finally, we know at this point here, vertically opposite angles are the same. So angle PXQ must be equal to angle RXS. And so the three angles of both triangles are the same. And so they're similar.
So question 16 is looking both at the bounds and the accuracy of a given value. So we're told that P is equal to the square root of 2e divided by f, e being equal to 6.8, correct to one decimal place, and f being equal to 0.05, correct to one significant figure. We're then asked to work out the upper bound on the value of P, correct to three significant figures. So if we're looking to find the upper bound, that means we want to find the maximum value of P that fits these constraints. And so looking at our expression, we want to maximize E because that's in the numerator and minimize F because that's in the denominator. So what is the maximum value of E we can use? What's the biggest value that's going to still round to 6.8? Well, it's going to be 6.84999 and so on, like with these nines recurring. Obviously 6.85 would round up to 6.9, so this is the largest value we can actually use. Minimizing F into one significant figure. Obviously, what's the smallest number that will round to 0.05? It's going to be 0.045. And so we then substitute these values we've got into our expression for P. So P equals square root of 2 times 6.84999. Now obviously, when using your calculator, you can just type in 6.85 and you'll get basically the exact same number. It's the accuracy that you'll need, but it's important that when you're writing down the working out, you'd write 6.849 recurring because that's obviously the correct value, divided by 0.045. And that's going to give us 17.4483, which obviously we're going to round to 17.4 for three different figures for our value of P. Question 17a looks at histograms. So we're given a table given the distance that some students live from school, so distance d miles, and then the frequency. And we're asked to plot this data onto a histogram. So the main thing to remember about a histogram, of course, is that the area of the bars is what represents the size of the data and not the height. And so before we can plot the histogram, we have to think about what the height's actually going to be for each bar. And that's obviously going to be width times height equals frequency. So obviously the width of the first interval, 0 to 1, is 1, and so the height just needs to be the same as the frequency, 90. So 1 to 1.5, we need the height to be twice the frequency, so 96. Same for 1.5 to 2, so 22 times 2, 44. 2 to 3 is just going to be the same as the frequency, so 8. And then 3 to 5, because that's too wide, we're going to use the height, which is half the frequency, so 6. Now that we know obviously our range of heights, we can sort of plot on appropriate y-axis demarcations and then plot the boxes. Question 17b continues on the theme of histograms. And so we're given another histogram that shows the distances in miles that Year 11 students live from school. We're told that the number of Year 11 students that live between 1 and 2 miles from school is n, and we're asked to find an expression in terms of n for the number of Year 11 students who live between 3 and 5 miles from school. So obviously we go back to that key idea that a frequency in a histogram is given by area, not by height. And so we can tell that we're going to have to compare the areas of the 1 to 2 box and the 3 to 5 box. And so if we count up, we can see there's 150 small squares in the 1 to 2 interval. So that's obviously equal to n. And we can see there's 60 small squares in the 3 to 5 interval. So our expression for the 3 to 5 is going to be n times 60 divided by 150, which is equal to 0.4n. Question 18 is a mix of a trigonometry question and a compound area question. So we're told that the base ABCD of the prism is a square of side 14 centimeters. T is the point on BC, such that BT TC is equal to 4,3. And the cross section of the prism is in the shape of a trapezium of area 147 centimeters squared. And we're asked to find the size of the angle between the line ST and the base ABCD, and to give our answer correct to one decimal place. So obviously this is a very complicated question, and what we know we're going to have to do in the end is isolate this triangle SDT, do some trigonometry, and find this angle STD. So the first thing we're going to do is we're going to try and find the length of this side SD, which we're going to do using the fact we know obviously 14 centimeters is the side length of every side of the base. So DC must be 14 centimeters. We know that RC is 12 centimeters, and we know the area of this face on the far side must be 147 centimeters squared. So using the trapezium area formula, we have 147 equals 12 plus SD divided by 2 times 14. If we work through this, we can obviously cancel out the divided by 2 to make just times 7. And then we can expand out a set of brackets to get 7 SD plus 84 is equal to 147. And so 7 SD is equal to 63. So SD is 9 centimeters. We can then find DT as the hypotenuse of the right angle triangle DCT. So using our knowledge of the ratio BT to TC being 4 to 3, we can find that TC is equal to 3/7 of BC, the whole side. And so TC is 6 centimeters. So we know obviously DC must be 14 centimeters. So because it's the hypotenuse DT, we do square root 14 squared, that's DC, plus 6 squared, which is TC, to find the hypotenuse. So that's 15.2315 centimeters. So we know that SD is 9 centimeters from our earlier discussion, and we know that DT is 15.2315 centimeters. So looking at the angle STD, we have the adjacent side length and the opposite side length. So we're going to need to use TOA. So that's tan of the angle is equal to the opposite divided by the adjacent, which we can rearrange to angle DTS is equal to arctan, or tan minus 1, of SD, that's the opposite, divided by dt, that's the adjacent. So arctan of 9 divided by 15.2315, which gives us 30.6 degrees as the size of the angle STD. Question 19 looks at mixed fractions. So we're given this expression 3x divided by x plus 2 minus 2x plus 1 over x plus 2 minus 1, and we're asked to rewrite it in the form ax plus b divided by x squared minus 4. So the first thing we want to do to combine these three terms, two fractions and one integer, into one term is get them all to have a common denominator. So we want them obviously all to have this denominator x squared minus 4. Now, of course, we can change around a fraction by multiplying its numerator and denominator by the same thing, which obviously is effectively the same thing as multiplying it by 1, and so we're not actually changing the value of the fraction. It's the same fraction, but it's just written in a different manner. And so to get the fraction with the x plus 2 denominator to have the x squared minus 4 denominator, want to multiply top and bottom by x minus 2, which we've done here. To get the second fraction to have that denominator, we need to multiply top and bottom by x plus 2. And to get the 1 to have that denominator, we need to multiply top and bottom by x squared minus 4. So as you can see, we've done this here. So we can go through each term. So multiplying the first one by x minus 2, we end up with 3x squared minus 6x as our numerator over, of course, x plus 2, x minus 2. For the second one, we have to multiply by x plus 2, so we get 2x squared, that's the first two terms, plus 5x, that's going to be the 2x times 2 and the 1 times x, and then plus 2, that's the 1 times 2. Obviously, again, divided by the same thing. At the end, obviously, minus 1, just going to be x squared minus 4, over obviously what is going to be x squared minus 4 as well. Now we want to collect up like terms, so obviously put it all together first. 3x squared minus 2x squared minus x squared minus 6x from here minus 5x, obviously this is a plus, but it gets minus here, and then minus 2 from here. Obviously again it's plus here, but there's a minus preceding it, plus 4, obviously because it's minus 4, and all divided by x squared minus 4. So again, now we're going to collect like terms. So in the x squareds, we have no x squareds because 3 minus 2 minus 1. In the x's, we have minus 6 minus 5, so minus 11x. And then minus 2 plus 4. In the irregular numbers, we end up with plus 2. Obviously, all divided by x squared minus 4. So in this case, a is equal to minus 11 and b is equal to 2. Question 20 looks at sequences. So we're told that the profit made by a shop increases each year. The profit made by the shop in year n is P subscript n. And we're told that the profit made by the shop in the next year, P subscript n plus 1, is going to be P subscript n plus 1 equals A, some constant, times P subscript n plus 800. And we're shown a table with the profit made by the shop in 2018 and 2019. So in 2018, the shop made £24,000 in profit, and in 2019, the shop made £29,600 in profit. And we're asked to work out the profit predicted to be made by the shop in 2021. So the first thing we need to do is find the value of A. So we're going to substitute in our values here. 2019 we're going to use as Pn plus 1, and 2018 as Pn. So in that case we get that £29,600 as 2019 profit equals A times £24,000 2018 profit plus 800. Now we're just going to solve for A. So first of all, we're going to subtract 800 from both sides. We're going to get A times 24,000 is equal to 28,800. And then we're going to divide both sides by 24,000 to get that A is equal to 28,800 divided by 24,000, which is equal to 1.2. So if we were to rewrite with our new knowledge this expression, we'd get that Pn plus 1 is equal to 1.2 Pn plus 800. So now we want to use this formula to extrapolate to 2021. So we're going to have to use it twice. Once to get the 2020 profit and once to get the 2021 profit from the 2020 profit. So first of all, the profit in 2020 is equal to 1.2 times profit in 2019 plus 800. We know profit in 2019 is 29,600, so we substitute that in, and we get that 2020 profit is £36,320. We then substitute this value back in, so 2021 profit is equal to 1.2 times 36,320 plus 800. So the profit in 2021 is £44,384. Question 21 looks at probability.
So we're told that Ray has got 9 cards numbered 1 to 9, and he's going to take out 3 of these cards randomly and work out the sum of these 3 cards and record the result. And we're asked to work out the probability that the result is an even number. So if we take 3 of these cards, how can we actually make an even number? So there's 2 ways to do it. We can either pull out 2 odd cards and an even card, or 3 even cards. Any other combinations will result in an odd number. So let's explore the probabilities of these sequences occurring. So if we do odd, odd, even, that can come in some different orders. We can either take out an odd card, then an even card, an odd card, an even card, then an odd card, or an even card and then 2 odd cards. It does say Ray takes out 3 of these cards, so you'd assume he sort of takes them out at the same time. But when we're doing these sort of probability questions, we have to assume that they're sort of taken out with a slight delay in between them to do the calculations. So, if we're looking at odd, odd, even, we can see initially there are 5 odd cards out of 9 total cards, so it's 5 out of 9 probability. Then we would be left with 4 odd cards and 4 even cards. So the probability of then taking another odd card is 4 out of 8. And then we'd be left with 4 even cards and 3 odd cards. So the chance of taking the even card then would be 4 out of 7. So obviously we assume these are independent events. And so to find the probability, we multiply these 3 fractions together and get 80 divided by 504. Looking at odd, even, odd. Again, to pick an odd number out of these 9 is 5 out of 9. We're then left again with 4 odd and 4 even cards. So the probability to pull out an even card is 4 out of 8. We're then left with 4 odd cards and 3 even cards. So the probability to pull out the odd card is 4 out of 7. So again, that's going to multiply to 80 divided by 504. And finally, to do even, odd, odd, initially there are 4 even cards out of 9. So that's the first probability. Then we have 5 odd cards and 3 even cards. So the chance of pulling out an odd card is 5 over 8. And finally, there'd be 4 odd cards and 3 even cards left. So the chance of pulling out an odd card is 4 divided by 7. Multiply those together, we get 80 divided by 504. Then looking at the possibility of even, even, even. There's initially 4 even cards out of 9. Then after that, there'd be 3 out of 8. Then after that, there'd be 2 out of 7. So multiplying these together, we get 24 divided by 504. Now, any of these different combinations can get an even sum. And so we want to add them together. When we're doing like a sort of an AND statement in probability, we want to add those probabilities together. So we're going to end up with 264 divided by 504, or to simplify, the probability of the sum being an even number is going to be 11 divided by 21. Question 22 looks at the topic of simultaneous equations. So we're told that L is the straight line with equation y equals 2x minus 5, and that C is a graph with the equation y squared equals 6x squared minus 25x minus 8. And we're asked, using algebra, to find the coordinates of the points of intersection of L and C. You must show all your working. Okay, so the first question you might be thinking is, why is this a simultaneous equations question? So when we say simultaneous equations, we're talking about 2 equations that could both describe the same, pair of x and y, or the same triplet of x, y, z values. So in this case, we're looking for instances where for these 2 equations, we can have one pair of, a y value and an x value that fit both equations. Sorry. And so on a graph, of course, this would be when these graphs intersect, because of course the y and x values are the same. So what we want to do is basically rearrange these equations and put them together so we can solve for either y or x, and substitute that value we get back in to find the remaining variable. So what I've chosen to do here is, obviously we've got a definition for y, 2x minus 5, so we're going to put it here into this equation. So 2x minus 5 all squared equals 6x squared minus 25x minus 8. We're then going to expand these brackets out, so we get 4x squared minus 20x, so that's minus 5 times 2, obviously done twice, plus 25 minus 5 squared equals 6x squared minus 25x minus 8. Then we're going to rearrange this equation to make a standard quadratic equation. So we're going to obviously subtract 4x squared from both sides, add 20x to both sides, and subtract 25 from both sides, which leaves us with 2x squared minus 5x minus 33 equals 0. If we now use the quadratic formula, of course, minus b plus or minus the square root of b squared minus 4ac all over 2a. We have 5 plus or minus the square root of minus 5 squared minus 4 times 2 times minus 33, all divided by 4 times 2. So we're going to simplify and clean this up. So 5 plus or minus the square root, obviously, minus 5 squared, 25. Minus 4 times 2 times 33 is 264. And of course, 4 times 2 is 8. Cleaning up a bit more, 5 plus or minus the square root of 25 plus 264, that's 289, divided by 8. 289 is 17 squared, so we're going to get 5 plus or minus 17 divided by 8. And so x is 22 divided by 8, or minus 12 divided by 8, obviously, using this plus minus. So x is 2.75 or minus 1.5. If we then substitute these x values into our the simple linear equation up here, we get that y is equal to 0.5 in the case that x is 2.75, or minus 8 in the case that x is minus 1.5. And so our solutions are 2.75, 0.5, and minus 1.5, minus 8.